Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session we shall see how to analyze an overhanging beam with the help of Kanis method. So here I have considered a problem where span AB is having an UDL of 3 kN per meter and a span of 12 meters, and span BC is carrying an eccentric loading of 18 kN, and span CD is an overhanging portion with a span of 3 meters carrying a point load of 6 kN at point D. The moment of inertia for span AB is 3.6 I, and for span BC is 1.8 I, and for span CD they have given 1.5 I. So from previous classes we know that the first step used in Kanis method is to calculate the fixed end moments. So if I consider the span AB which is having an UDL, so if we are coming from left to right, it will be negative from left to right. So minus, the formula is WL square upon 12. So the load here is 3 kN per meter. So minus 3, and the total span here is 12 square upon 12. We are having an answer of minus 36 kilonewton meters. So if we need to find fixed moment from B to A, the formula remains same. Now we are coming from right to left. Only the sign changes, which is plus WL square upon 12. That is plus 3 into 12 square upon 12, which will be equal to plus 36 kilonewton meters. Same way for span B to C, fixed moment from B to C, since it is carrying an eccentric loading and at a distance of 6 meters from point B, the formula is minus WA B square upon L square. W here is 18, so minus 18, and the distance A here from point B is 6 meters and B is 3 meters. So 6 into 3 square divided upon the total span here, the span L square, that is 9 square, which will be equal to minus 12 kilonewton meters. So next, fixed end moment from C to B will be plus WA square B upon L square. So W here is plus 18 into A here is 6 meters, so 6 square into 3 upon 9 square, which will be equal to plus 24 kilonewton meters. So now if we want to find out the moment for the span CD, which is an overhanging portion, for span CD, so at the free end here it is carrying an point load of 6 kilonewton and the span here is 3 meters. This is point D, this is point C. So coming from left to right, it is negative. So moment from C to D will be equal to, considering moment about this point, that is force multiplied by perpendicular distance, minus 6 into 3, which will be equal to minus 18 kilonewton meters. So if we observe here at point C, I'll write the representation here. At point C, from C to D it is minus 18 kilonewton meters, and from C to B we have got here, which is plus 24 kilonewton meters. So since the moments are not equal and opposite here, we need to go for the balancing of moments about this point here. So moment from C to B will be equal to, so to balance the moment about this point, we need to consider an additional moment. So here the fixed end moment we have got is plus 24. So if I want to balance the moment, I will consider an additional moment, that is minus 6, which will be equal to plus 18 kilonewton meters. So now from C to B also, if I add an additional moment over here, that is minus 6 kilonewton meters, this will be equal to plus 18 kilonewton meters. Now the moment from C to B is also 18 kilonewton meter, and C to B is also minus 18 kilonewton meters. From moment distribution method, we know that whatever the additional moment we have considered here, half of that value has to be carried to the other end of the same member. So the moment from point B to C here is how much? This is the fixed end moment, minus 12 plus half of the additional moment, whatever we have considered here, we have to take into consideration, that is minus 6. The value will be equal to minus 15 kilonewton meters. So now if I want to write the modified fixed end moment or the final fixed end moment, so this is the modified fixed end moment. So from A to B, it remains same, which is minus 36 kilonewton meters, and from B to A, it remains same, plus 36 kilonewton meters. So from B to C, so fixed end moment from B to C, what we have considered here, that is minus 15 kilonewton meters. So from C to B, we have calculated here, that is plus 18 kilonewton meters, and from C to D it is minus 18 kilonewton meters. So these values we have to consider while we are calculating the final end moments. So after calculating the fixed end moment, the second step will be to calculate the stiffness, which is represented by K, and a rotation factor, which is represented by U. So if we need to calculate the stiffness and the rotation factor U, let us consider a table here where I will consider the joint, and for that particular joint we will consider the members, and then we will consider the stiffness for that particular member, and then the total summation of the stiffness, then U, which is calculated by minus half into K by sigma K. So here if I want to consider the joint here, if you observe, we are having two joints here, that is B and C. So joint B. So if I consider the joint B, B is connecting for A and similarly for C. So at joint B we are having two members, B to A and B to C. At joint C here we are having two members which is connecting from C to B and C to D here. So if we need to find out the stiffness here, to find the stiffness we need to consider the far end conditions. So if I take the member BA here, B is the near end and A is the far end here. If I see the condition of the far end here, the far end is fixed here. Whenever the far end is fixed, the stiffness is equal to I by L. So the moment of inertia we have taken here, that is 3.6I upon the total span here, that is 12 meters, which will be equal to 0.3I. So same way, if I want to consider the stiffness for member BC. See, if you see here, B is the near end and C is the far end, and since C is a simple support here, whenever we are having a support other than fixed support, the moment of inertia will be equal to 3 by 4 into I by L. So here the moment of inertia they have given, that is 1.8 I upon the length, the total span here divided by 9, which will be equal to 0.15 I. So if I take the summation of these two, we are going to get the total stiffness here, which is 0.45 I. So now if I consider the value here to find out the rotation factor, where U is equal to minus half into K upon summation of K, if I put the values here for member BA, we are having a value of minus 0.333, and for member BC, the rotation factor here is minus 0.167. So now, if I want to calculate the stiffness about the member CB here, see here, C is the near end and B is the far end here. Since B is an intermediate support, in structural analysis, even the intermediate support also we are considering it as a fixed support. So for fixed support, the moment of inertia is I upon L, which will be equal to I, what we have got here, it is 1.8 I upon the total span here is 9 meters, which will be equal to 1 I. So from C to D, since C to D is an overhanging portion here, the stiffness is 0. So this entire rotation factor for the member CD becomes 0. So now if I take this one, the summation here is how much? Here it is 1 I. And if I apply the values over here to find out the rotation factor, I am going to get the value of 0.5 I. Sorry, it is only 0.5. So step 3 will be to calculate the rotation contributions. So for that I have considered a table here, which is also called as a Kanis table. So what we have done here is we have just replaced the intermediate support with the help of a box here. So this is point A, this is point B, this is point C, and this is point D over here. Since we are having only one intermediate support, I have taken the box over here at point B. So whatever the fixed end moment we have got in the first step, we have to represent here in this table. So fixed end moment from A to B, we know we had got, that is minus 36 kilonewton meter. I will write only the values and not the units here. So from B to A, we have got plus 36 kilonewton meter, and from B to C, we have to consider the modified fixed end moment, which is minus 15, and from C to B, it is plus 18 kilonewton meter, and from C to D, it is minus 18 kilonewton meter, and about point D, it is 0. So now what I have to write here in this, inside this box, is I have to take the summation of the fixed end moment about this point B here. So that is fixed end moment from B to A and from B to C will be the summation of the fixed end moment about this point here. So plus 36 and minus 15 will be equal to plus 21. And here inside this box we have to write the rotation factor, whatever we have got in the table 2 in the step 2, that is from B to A we have to represent here, and from B to C we have to represent the rotation factor here inside this box. So we know the rotation factor from B to A we have got is minus 0.333, and the rotation factor from B to C we have got minus 0.167. So using these values, I need to calculate the rotation contribution, where the rotation contribution, I will take it as small m dash AB, here M dash B A, this point will be M dash B to C, this is M dash C to B, this is M dash C to D, and this is M dash D to C. So whenever we are considering the rotation contribution, we know that the formula, if we need to find out the rotation contribution about any point, which will be equal to the rotation factor multiplied by the summation of fixed end moment plus summation of far end rotation contributions. This is the formula. So now, since we are finding out the rotation contribution only for the intermediate supports and not for the end supports, so at the end supports, the moment or the rotation contribution will be equal to 0. So now I need to find out the rotation contribution only about the intermediate supports, means that is M dash BA and M dash BC. So if I want to consider the rotation factor about this point, about this joint here, the far end rotation contribution, that is this one, we have to take into consideration, that is M dash AB for this point and M dash CB. This value we have to consider for the far end rotation contributions. So if I go for the first cycle or the iteration process, if I consider this, that is M dash BA, which will be equal to the formula we know, the rotation factor. So from B to A, the rotation factor we have calculated here, which is minus 0.333 multiplied by the summation of fixed end moment. So this is the fixed end moment, the total summation whatever we have got, which is plus 21 plus summation of far end rotation contribution. The far end rotation contribution here is 0 and here is also a 0. So 0 plus 0, which will be equal to, we get a value of minus 6.99 kilonewton meters. So this value will represent here, which is minus 6.99. So next, if we need to find out the rotation contribution about this point, M dash B to C, here the rotation factor is minus 0.167 multiplied by the summation of fixed end moment, that is plus 21 plus 0, which will be equal to minus 3.51 kilonewton meters. So we can write the value here, which is minus 3.51 kilonewton meters. So if we go for another cycle also, since the values remain same, we are going to get the same values. So we can stop the iteration process at this point here itself. So the moment, so the rotation contributions about this point, M dash BA we have got here is minus 6.99 and M dash BC we have got it as minus 3.51. So using these values, our last step will be to calculate the final end moments. So calculating the final end moments, the last step here, that is step 4, which is the calculation of final end moments. So we know whenever we want to calculate the final end moments, that is here, that is from MAB, the formula we know, which will be equal to the fixed end moment from that point, that is fixed end moment from A to B plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. This is the formula. So fixed end moment, how much we have got here? That is minus 36 plus 2 into the 2 times the rotation contribution about the near end. How much here it is? Here it is 0 plus the rotation contribution about the far end. How much we have got here? Minus 6.99. So we have to consider here minus 6.99, which will be equal to So minus 42.99 kilonewton meters. Same way here, if I consider moment, final end moment from point B to A, that is fixed end moment from B to A plus 2 times rotation contribution about the near end plus 1 times rotation contribution about the far end. So fixed end moment from B to A, how much we have got here? Plus 36 plus 2 times the rotation contribution about the near end. The near end here is m dash BA. The value is minus 6.99 plus 1 times rotation contribution about the far end. The far end rotation contribution is 0. So final end moment from point B to A will be equal to 22.02 kilonewton meters. So same way, if we need to find out the moment, final end moment from point B to C. So final end moment from B to C, we have got fixed end moment from B to C. Fixed end moment from B to C plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. So the fixed end moment from B to C, how much we have got here, which is minus 15 plus 2 times rotation contribution about the near end. Near end here, how much we have got? Minus 3.51 plus 1 time the rotation contribution about the far end, how much? It is 0. So final end moment from B to C will be equal to minus 22.02 kilonewton meters. And the moment about point C to B, final moment from point C to B, we know it is plus 18 kilonewton meter, and the final end moment from point C to D, we know it is minus 18 kilonewton meters. So representing these values over here, so from A to B, how much we have got? The final end moment we have got here is minus 42.99 kilonewton meters, and from B to C and from B to A we have got here is plus 22.02, and from B to C we have got minus 22.02. So we can see here about this point B, the final end moment are equal and opposite directions. That means our calculation is correct. So from C to B, how much we have got here? We have got here it is plus 18 kilonewton meter, and from C to B we have got minus 18 kilonewton meters. So using these values, we can calculate even our support reactions and maximum bending moment. So similarly, we shall see some more numericals related to Kanis method in the coming classes. Thank you.